right, so we are halfway through chapter 7. And so what we're going to be hitting up now is all about what we call the Central Limit Theorem. Central Limit Theorem. That's what 7.3 is all about. So let's dive into the Central Limits Theorem. I don't know why I call it limits. Is it really limits? I thought it was limit. Let me just double check that real quick. Oh gosh. Almost there. And it says that it is the central limit. I don't know why I pluralized it. That's wrong. Central limit theorem. Silly Mr. Armstrong. Or what we also call CLT. Okay? Get rid of that extra S. So central limit theorem. So, central limit theorem. First thing, before you can even apply it, it has 3 conditions. Very much, like what you saw when we did the standard error. And it had 2 conditions. So central limit theorem, CLT, has 3. So in order to use this, the sampling distribution must meet the following 3. In other words, the way you're taking your sample, the way you're getting your survey done. Okay? So 1, it must be random and independent. So hopefully, you are randomly selecting how this information is coming in. But the big thing is it must be independent. With or without replacement, it doesn't really matter again. Independent means that the decision of one person and how they answer you does not affect the decision of another person. Okay? So if you're at the mall and you're interviewing someone that's coming out of Old Navy, their answers cannot affect someone that comes out 5 minutes later. 5 minutes later, their answers to your sampling or your survey, as we should say. Okay, so the first person that comes out, their answers cannot affect someone else's answers later on. That's what it means to be independent. Okay, everybody answers of their own free will, with beyond any other influences. Okay. So, give you another example, just kind of a tangible one, if that one kind of like flew over you. If I come to class and I have a deck of cards and I come up to one student in our class and say, draw a card. They pick a card. Okay. And I have them put the card back in. So that would be with replacement. And I shuffle it and I go to the next person and I say, draw a card. That means the first student that drew a card and got whatever it was, and then the second student that drew a card and got whatever it was, they didn't affect each other. They both had the same chances of drawing whatever card they wanted. That's independent. One does not mess with the other. Okay? So that's super important. All right. Second condition. That the sample size is large enough. And what you're seeing here is this is your sample proportion. And what you're going to do is you're going to take that sample proportion times the total amount of samples you have. And you need to make sure that you have at least 10 successes. That's what this is all about. So your sample size needs to have at least 10 successes. And then over here, this is your sample size having at least 10 failures. Okay? So that's what it means to have a large sample. You got to have at least 10 successes and at least 10 failures. And that's what this is. This is your sample proportion happening. This is your sample proportion not happening. So if you take your sample size times the not, hopefully we have at least 10 failures. If this isn't met, we don't have a large enough sample size. Okay? So you take your total times the sample proportion, better be greater than or equal to 10. You take 1 minus your sample proportion, which gives you the not sample proportion. If you kind of remember that from college mathematics, it's the complement. So if I take my total times the complement, I better have at least 10 failures. Okay? And then last but not least, our sample is random, independent, large. Our population must be large. Okay? Our population must be large. And again, we only do this without replacement. We check it. Okay? And so what we hope is our population is greater than or equal to 10 times our total, the total number of people we talked about. Okay? So as long as these three are met, random and independent, a large sample, and a large population, and again, most of the time we're working without replacement anyway, so you're going to be checking all three. As long as those three met, we can apply the central limit theorem, which means that your sample is close to a normal distribution. Your sample is close to a normal distribution. Okay? Meaning it's got that nice symmetric curve to it. Okay? We talked about that normal distribution all the way back in 6162. That's where we talked about all that stuff. So now it's coming back to us. Okay? Which means that your sample, or excuse me, your population portion and your population standard error, or standard deviation in this case, because they're both the same, can be used on the normal curve. Okay? And again, if we don't know the population information, so we don't know the population proportion, we don't know the population standard deviation, because usually we don't. If we don't know that, we can also change it for p hat, your sample information. Okay? So that's basically what it allows us to know. That if we do a sample, okay, a sampling distribution, if my sampling distribution meets all these requirements, we can relate it back to the normal. Okay? All right. So let's talk about what's going to happen in your assignment, because that's all 7.3 is. It's just applying that information. Okay? So it says return to exercise 7.25 and write down here, this was exercise 7.25. We did it in the video for 7.2. Yeah, 7.2. And remember that the answer to this was that we expected 20% and give or take, I believe it was 4%. If I'm not mistaken. Let me just double check that. So we're just running that standard error. So 0.2. Oops. Sorry, I'm just working on my calculator real quick to double check that. Putting in my fraction, 0.2 times 0.2 all over 100. Yeah, 4%. Okay, so these were the two answers from A and B right here, just so you know. So this is what we knew back in that example. We expect 20% of the orange candies to give us, give or take 4%. Okay, so now what they want us to do, they want us to find the approximate probability that the random sample of 100 will contain 24% or more. All right. So let's talk about how we do this. Okay. So the first thing you're going to want to do is you need to check CLT. Okay? You need to check that. All right. So my sample is definitely random, and it's definitely going to be independent. Okay? So we definitely have the first piece checked. Draw, you know, selecting 100 candies. If I select 100 candies and then go back and select another 100 candies, my first selection does not affect the second selection. I'm just picking up 100 candies. It doesn't matter. Okay. So that's why it's definitely independent. And it says random. So we know that that's done. So the first thing we got to check is we got to make sure that there is at least 10 failures and 10 successes. Okay. So that's what you saw over here that we are talking about right here. Okay. And so that means you need to know what p hat is. Well, let me tell you some things that you already know. All this information that we got from 7.25, this is your p. This is your SE. Okay. So up here, this 24%, that's p hat. Okay. So now that you know everything. So this stuff that's down here, everything that we dealt with back in this example, this is P and this is your SE. This is your population information. So we actually know that. Okay. Now, this is the P hat. So if we want to talk about failures and successes, this is what it looks like. I don't know why I was putting a P there. We're going to take N, which this guy is N right here. You can see your N right there again. It's the same in both. And we want to take N, which is 100, times P hat. But again, this is a percentage, so it needs to go in as a decimal. So times 0.24. We want to make sure this is greater than or equal to 10. Okay? So if you take 100 times 0.24, you get 24. Greater than or equal to 10. So this definitely meets. I have 24 successes. Okay? Then the other one you check is the failure. So we want to make sure that if we take 100 times 1 minus 0.24 is greater than or equal to 10. Okay? So you just go to your calculator, 100, parenthesis, 1 minus 0.24, parenthesis, enter. That gives you 76, greater than or equal to 10. And that definitely meets. So our sample size is large enough. Okay? Our sample size is large enough. So we meet the random and independent. We meet the sample size. So the question is now we check the population. Okay? And you can easily check the population. So if you think about this, our population I'm just going to abbreviate it POP. We want to make sure that N is greater than or equal to 10 times our sample. Okay? N is greater than or equal to 1,000. So my question to you is, remember this is all about a package, and packages have 100 random candies. So do you think our population, or sorry, a package, okay, of milk chocolate M&Ms, and suppose we examine 100 candies. All right. So our question is, we've got all these packages that have M&Ms in them. Do you think our population of packages with M&Ms will be greater than 1,000? I hope so. Okay, definitely. Most of the time, you're not going to know N, but you have to think about what it is the population that you're looking at. And our population is packages of M&Ms. Okay? Do you think our packages of M&Ms enough out there that we have over or equal to 1,000 candies? And we definitely do. So we know that the population is being met because I guarantee you there are over 1,000 packages out there. Okay, and there are tons of M&Ms in one package. Okay, tons of M&Ms. Actually, if I remember correctly, in a king size bag of M&Ms, a king size package. Okay, there should be roughly 100 M&Ms in each king size package. Okay, it averages to roughly 100% or 100 M&M candies in a king size package. So definitely gonna meet this. No worries. Okay, so because we meet all these criteria, random, independent, large sample, large population, we definitely meet CLT, and we can relate this to a normal distribution. Normal, where our p hat, or sorry, not our p hat, our population portion is 0.20, and our standard error or our standard deviation is 0.04. Remember that notation? This happened to be the mean, and this happened to be the standard deviation. Okay? Or this was like our mu, and this was our sigma when we talked about this. Okay? So there we know that. So that's good. That's all a part of part one. And so this is our normal distribution information because that's also a part of part one. So once you check this, after you do that, and you're going to get the normal distribution info. Okay? And we actually did know P and our standard error. P 1 minus P all over N. Okay? We got that information from the 7.25. That guy right there. Okay? So all we do now to find our probability is we want to answer this question. We want to know what's the probability when, P hat, or no, P is greater than or equal to 0.24. That's what we're after. We want to know that information right there. Okay? Let me just double check that, make sure, because this is an example that you're going to see in your assignment. I want to make sure that I knew it. It was P hat. We want to know when P hat is greater than or equal to 0.24. So remember back in 6.2, I taught you a couple ways to do this. You can do it by hand. You can use the TI-84, or you can use StatCrunch, which I didn't bring up StatCrunch. I should have. I'm just all over the place in this video today. So let's bring up StatCrunch real quick. Should have had it up, but silly Mr. Armstrong, just not thinking. Give it a second. It's thinking about life and all its life choices. There we go. StatCrunch. We selected it. Come on. StatCrunch. There we go. Open. Again, life choices. Come on, StatCrunch. There we go. There we go. Now we're moving. Now we're playing with power, opening it up. And show me that yellow tab again. There it is. Open StatCrunch. Now we're in. All right. So again, in order to find this information, we're going to go to, I believe it was calculators. Yeah, calculators and normal. And then we're just going to put in, come on, you, our information. So our mean was 0.2. Our standard deviation, 0.04. We want to be greater than 0.24. Compute. And there it is. So our probability for this would be 0.158655. So let's round it to 4 decimal places. So 0.1587. Oh my gosh, I forgot the most important thing. We need to convert these into the z-score. It's so weird. I don't know why I didn't think about that. Okay. So I forgot that we needed to convert that into a z-score. So I was talking about converting to a z-score. Sorry, I paused the video for a second, so because I wanted to double check something. You actually don't have to convert to a z-score if you want. This is the answer, 0.1587. So if we come back here, equal to 0.1587, which if we turn that into the percentage, it would be 15.87%. Okay. Now, again, this is if you wanted to work it just like this without actually throwing it into the standard normal. So if you wanted to actually use the table and do the standard normal, because remember, standard normal looks like this. The standard normal, you're in, and then you are 0, 1. This is where you would need to turn into the z-score. Okay. So you would take, to find the z-score for this, p hat minus p all over the standard error. Okay, so that would be 0.24 minus 0.2 all over 0.04, and the answer is 1. So what you'd be looking here is the probability of when your p hat was greater than or equal to 1 standard deviation. Okay, and if you go into StatCrunch, you can do that too. So we can change this up and do standard normal. So 0, 1, 1. Oh, same answer. Okay, so you have 2 ways that you can kind of look at this. I think it's important that I show you both. Okay, so if you want to work with it with the original population portion and standard error, and then this is your p hat, your sample proportion, or you can convert it into the standard normal, and all you would do is convert this guy into its standard deviation and look at what you're dealing with. Okay, so your call on that. Lots of ways to work this. Okay, so your call, because it will match either way. If you did your calculator, I still haven't learned the draw feature on this yet for this, but you don't really need the curve when you deal with this anyway. Remember, hit second distribution, and you want to come down to normal CDF. Okay, so we are looking for greater than. So this is where we're going to put the 0.24. And the upper will be that positive 1 scientific notation e to the 99. And then for your mu, you're going to put in the 0.2. And then sigma will be the 0.04. Scroll down to paste, hit enter, and there it is. Okay, or again, you could do the standard normal. Go down to CDF, change this to 1, keep the upper. This is now 0, this is now 1. And paste. Same answer. Okay, so it's taking the central limit theorem and it's taking what we did in chapter 6 and putting it all together. That's really what 7.3 is. Okay, let's do some more. All right, let's do some more. So again, you got the same answer here as what you did right there. And that's what it's after. Once that probability, it'll either ask for it as a percent or it will ask for it in the decimal form. Just make sure that you read the fine print on what it wants. Okay? So go ahead and try this one out on your own. And go. Okay. So let's go back through this. Oh, I didn't tell you what. So after you did this part, okay, your step 2 could be to find the z-score. All right, after you check the conditions, your step 2 is to find the z-score if you wanted. Or you can just go straight into step 3, which is run the information with the table or your technology. Remember, in order to use the table, if you're doing it by hand, you have to know the z-score. In order to use the table, you have to know the z-score. Okay? Other than that, you can use your technology. All right, let's do this again. So on this one, right here, this 65, that's P. They don't tell us the standard, the standard error in this. You would actually have to figure that out. Remember, standard error is equal to the square root of P times 1 minus P all over N. Okay? So that's your standard error. If you want to go that route, you don't have to, because you could also do the standard normal. You don't even need that piece of information. All right? So we're going to find the approximate probability that at least 67% of 200 randomly sampled people taking the bar exam will pass. Okay? So in the end, what we're looking for is the probability that P hat is greater than or equal to 0.67. That's what you're looking for in the end. All right? But before we can do that, we need to check CLT. So obviously this is random sampled. So that's good. And one person taking the bar exam does not affect another person taking the bar exam. So we know it's independent. Okay? If I took the bar exam, my score does not affect whether you pass or not. So definitely independent. So condition 1, check. Condition 2, let's check successes and failures. Okay? Success, failures. Okay? So we're going to take 200 because that's our N. Okay, it's right here. This guy, well, that was supposed to be in red, but that's all right, is N. And we're going to multiply that by our p hat 67. Is this greater than or equal to 10? So 200 times 0.67 gives us 134. That's definitely greater than 10. So check. And then we'll take 200 times 1 minus 0.67. Is that greater than or equal to 10? So 1 minus 0.67 gives us 0.33 times 200, 66. And that's definitely greater than or equal to 10. So we pass condition 2. And then the question is our population big enough? So is n greater than or equal to 10 times 2,000 or 200? Which the question is our population bigger than 2,000? Okay. So what is our population? We are talking about people who take the Oregon bar exam. So do you think there have been at least 2,000 people that have taken the bar exam in Oregon? Now we're talking about all the way through time here. Anytime this Oregon bar exam has been given, do you think we have 2,000 people or more? And yes, we do. Okay. You definitely have over 2,000 people. What? I don't. Let's see here. And you can double check this. Go to Google and be like, how many people have taken the Oregon? Not Oregon. Not Oregon. Oregon. This is why I'm a math teacher, not a spelling teacher. Okay. I knew there was an E, just couldn't remember. Oregon bar exam. Normally, about 260 people pass the July bar exam. That's just July. Okay. So, if that's just July, obviously, if that, take and consider there are 12 months, yeah, you definitely have over 2,000 people taking this. Easy. Okay. So you can always double check yourself. But you use your common sense. Yeah, definitely. Throughout the history of the bar exam being taken in Oregon, there's definitely been over 2,000 people. All right. So CLT is met. CLT check. So you can do one of two things now. Okay. You can go through and figure out the normal distribution. Okay. So normal distribution. We already know what P is. It is 0.67. Okay. Or sorry, 0.65. We can figure out the standard error real quick. You just go up here and, as I said, to find that standard error, all you'd be doing in the calculator is taking 0.65 times 1 minus 0.65 and dividing that by 200. So if we take 0.65, using my calculator, 0.65 parenthesis 1 minus 0.65 parenthesis 200, that gives you this as a decimal. 0.00111375. So we can put that number in down here. So I actually have it on my calculator still. So 0.001137.5. So there's the normal distribution if you wanted to use it, or if you did the standard normal, you don't have to do any of that and just call it n 0, 1. Now, if you're doing the normal distribution, you do not have to turn 0.67 into a z-score, okay? Because we have this information right here, you can now go figure out the answer using technology. So greater than or equal to 0.67. You're ready to go. If you wanted to do the standard normal, then this is where, again, you'd have to turn this 0.67 into a z-score. Okay? So you would take 0.67 minus 0.65 and divide that by the standard error, which is 0.001137.5. You see why I don't want to round. Okay, because if I rounded that and then I do that in here, then it's going to lead to even more rounding error. So 0.67 minus 0.65, and then divide that answer by the 0.001137.5. And you get 17.5824175.8. That's what my calculator kicked out. So basically 17 standard deviations above. All right, so let's take a look at what we know. Let's figure out what our answer is. Again, I like to use StatCrunch. I'm not going to really go back to the calculator. I like me StatCrunch. So all I got to do is come in here, and I can put in the 0.65, and I can put in the 0.001137.5. And then down here, I'm going to be greater than 0.67. So it's practically 0. Okay? It is practically 0. All right. So then the next one, I mean, if we take a look at this, and that makes sense, thinking about what that standard deviation was. If I put 1 here, I go in here and I put in the 17.58241.758. Again, it gives me 0 because it's way, way up here. It's all the way out here at 17. Okay? So what's the probability of 67% or more passing? It's practically 0. Okay? All right. So go ahead and try this one on your own. Pause the video. Oh my gosh. Sorry. I need to go back to that problem. I forgot to do something. I forgot to take the square root of this. Oh my gosh. Most important part. I can't believe I forgot that. Oops. 0011375. Go out here, delete the rest of that. So I'm mistaken. I am mistaken. This guy right here, I got to take the square root of that, which gives us 0.033768439. Which changes this piece and will also change my z-score over here. So this was 0.0, oops, that looks like a 6. I'm so sorry for this. You probably caught my error even long before I finished the problem. 268,439. And then that changes this guy down here, which changes our z-score. So this changes a lot of information. I'm so sorry about that. 0.0337268,439. So let's go back and let's fix this piece. So 0.2 divided by our new standard error gives us, this is much better, 0.5929994535. So let's fix this because of my dumb error. So if I go back and do this, 0.65, but in the new standard deviation, the new standard error, 0.033768439. Then this guy, 0.67. There we go. So a little better odds this time. A little bit better. So about 20 or 0.2766. I knew something seemed a little weird about that. I was like, I don't remember this ever being that. So this was 0.2766 or 27.66%. And if we do it the other way with the standard normal, now that I have everything correct, I can't believe I forgot to take that square root. Make sure that you follow through. 1, and this guy will be the 0.5929994535. And it should be the same answer. Yes, it is. There you go. I'm sorry. I'm only human, though. I make mistakes. So this guy gives us the same information. And there you go. So your choice on what you want to do. You can either keep it in that, normal distribution, or you can change it into the standard normal. Your call. All right. So this is the last question. Again, all the assignment is just like what we were talking about. So hopefully you paused it, you've done this. It says, before doing any calculations, determine whether this probability is greater than 50% or less than 50% and why. All right. So if you think about this, it says there was an article mentioned in 7.41 that also reported that 25% of the residents of Huntington Park lived in poverty. Okay. Suppose a random sample of 400 residents in Huntington Park is taken. We wish to determine the probability that 30% or more of our sample will be living in poverty. So if you look at this, our probability in this should be greater than 50, or sorry, I was thinking something else. Less than 50%. I'm making all sorts of craziness today. Because if you're thinking about this curve and that it's normal, Okay. In the middle is what percentage? 0.25. And remember that this represents half the data. Half is below, half is above. Where is 30% in relation to this? It's above it. That would be 0.3, which would be less than 50%, because 50% is either below this or above this line. Okay? From this line is your 50% mark. So 30% is above it, so it's going to be less than 50% because this percentage is above the halfway mark. Okay? Again, all this is like, um, fill in the blank, or this guy is like a multiple choice, just like everything else. You're not actually typing in the answer Y. Okay, so now it wants us to calculate. And again, it wants us to make sure, actually it says assume the sample is collected in such a way that the conditions for using CLT are met. Okay, so we don't have to worry about checking CLT because it says everything is met. But if you had to check it, you know what to do. Okay, you would take the, you would check successes and failures. Nothing crazy there. What is our sample size is N. This is our P. This is our P hat. Okay. So we would be taking 400 times 0.3, which 400 times 0.3 is 120, and that's definitely greater than or equal to 10. And then you'd be taking 400 times 1 minus 0.3. So 400 times 1 minus 0.3 is 280. And that's definitely greater than or equal to 10. Our population size, N, is it greater than 10 times 400? And so the question is really, is the population of Huntington Heights, isn't it Huntington? Huntington Park, sorry, not Heights. Is it greater than or equal to 4,000? So I don't know how big Huntington Park is, but they're allowing us to assume that, yes, this population is either equal to this or bigger than it. Okay? And then, of course, we know that our sample is random and one person's poverty does not affect another person's poverty. Okay? So definitely independent. But you get to assume all that. But I just did a quick check of it just to remind you of everything that's going on. I think it's important that you see that because these steps, you're going to see this coming up more and more as we move on to other sections. Okay? So we want to check this for our answer. We want to know what's the probability that P hat is greater than or equal to 0.3. So you have those two methods. You can either do N of 0.25, comma, your standard error figured correctly this time, second square root, alpha y equals, for my fraction, 0.25, parenthesis 1 minus 0.25, parenthesis all over 400, is 0. And I made sure I put the radical in this time, 0.0216506,351. And so now you could go into your technology and put that information in. Okay? Because this is your P hat. Or, again, you could do the standard normal 0.01. But you'd be looking for the probability of p hat being greater than or equal to, well, you're going to take 0.3 minus 0.25 and divide it by that standard error right there, which gives you 2.30940106. So there would be the z-score. So you do either one. So let's find our answer. P hat greater than or equal to 0.3 equals. So I've already kind of got this set up for the standard normal. So let's just go ahead and change out what we need to know. So this is 309.401076. So there it is. There is our percentage. Okay. So really close to basically 1%. All right. So 0.010. 0.010. Or in other words, 1.0%. Actually, I should have 4 decimals. Why do I not have 4? Let me go back. So, come on, you. Oops, wrong thing. You don't want that. That's my email. 0.0105. Should be a 5 here. Okay. And again, I did that using the standard normal. You get the same answer if you do it the other way. So if we come in here and we change this to the 0.25, and we change this to the 0.021506,351. And this guy down here becomes the 0.3. Enter. Okay. And that is the central limits theorem. It allows us to take surveys that we perform, okay, sample distributions, and relate them back to the normal curve. That's the central limit theorem. As long as you meet those 3 criteria, random and independent sample, you got to have at least 10 successes, at least 10 failures, and most of the time it's without replacement, so you check and make sure that your population is greater than or equal to 10 times your sample size. And right here are the questions for 7.3. Enjoy. Have fun. Sorry for all the mistakes. Hope you can forgive me.